In one of the most monumental discoveries of the 20th century, we learned that the universe is not simply a static, unchanging background, but rather that space itself expands as time marches on. It's as though the very fabric of the universe itself is stretching so that distant objects get farther and farther apart. We see this phenomenon in all directions and in all locations in space when we look beyond the local group. Regardless, nearly 100 years after it was all worked out, it's still a puzzling, counterintuitive phenomenon, even for experts in astronomy and astrophysics. It's only natural to wonder, if the universe is expanding, what exactly happens to the fabric of space itself while this process occurs? Is the space itself stretching, as though it's getting thinner and stretched out? Is more space constantly being created, as though it were filling in the gaps that the expansion creates? And if the universe has been expanding for all this time, what is it that the universe is expanding into? Are we expanding along with the universe? This is one of the toughest things to conceive of in modern astrophysics. Fortunately, the latest data from James Webb are providing new insights that help shed some light on these mysteries. Join us as we explore what's exactly going on. Theoretical beginnings. The starting point of our conversation has to be general relativity, our modern theory of gravity first put forth by Einstein. General relativity, at its core, is a framework that relates two things that might not obviously be related: the amount, distribution, and types of energy, including matter, antimatter, dark matter, radiation, neutrinos, and anything else you can imagine, that are present all throughout the universe, and the geometry of the underlying spacetime, including whether and how it's curved, and whether and how spacetime itself will evolve. If we inhabited a completely empty universe, or a universe that contains nothing within it at all, no matter radiation or energy of any form, you'd get the flat, Newtonian-like space you're intuitively used to, something that's static, uncurved, and unchanging. But what if we then considered the absolute simplest case of a non-empty universe? If instead we were to put down a point mass in the universe, we'd find out that space was curved in a particular way, Schwarzschild space. Any test particle that we'd put down onto our universe would be compelled to flow toward that mass, following a particular trajectory. And if we were to then make our physical situation just a little bit more complicated, by putting down a point mass that also rotates, we'd get space that's curved in a more complex way, according to the rules of the Kerr metric. It will have an event horizon, but instead of a point-like singularity, the singularity will get stretched out into a circular, one-dimensional ring. Again, any test particle you put down will follow the trajectory laid out by the underlying curvature of space. These spacetimes are clearly much more complicated than a spacetime that's simply flat. However, they are still static in the sense that any distance scales you might include or measure, like the size of the event horizon or the distance between two arbitrary points within this spacetime, don't change over time. If we could somehow exit a universe with this spacetime and return to it later, whether a second, an hour, or a billion years later, the structure of this spacetime would be identical, irrespective of when we return to it. In spacetimes like these, there's no cosmic expansion that's present. There's no change in the distance or the light travel time between any points within this spacetime. With just one or fewer sources of matter inside and no other forms of energy, these model universes really can be static. Expansion and contraction of the universe. But it's a very different game when you choose not to put down isolated sources of mass or energy, but instead to fill your universe uniformly with stuff everywhere. In fact, the two criteria we normally assume about our universe, and which are strongly validated by large-scale observations, are called isotropy and homogeneity, in which isotropy tells us that the universe is the same in all directions. Everywhere we look on cosmic scales, no direction looks particularly different or preferred from any other. On the other hand, homogeneity tells us that the universe is the same in all locations. The same density, temperature, and expansion rate exist to better than 99.99% precision on the largest scales. As far as we can tell, our universe, on large cosmic scales, is indeed both isotropic and homogeneous. In this case, having a universe that's uniformly filled with some sort of energy, the rules of general relativity not only mandate that the universe must evolve, they tell us how. The equations that govern the evolution of the universe are known as the Friedmann equations. Derived by Alexander Friedmann all the way back in 1922, a year before we even discovered that the largest, most prominent spiral in the sky, the Great Nebula in Andromeda, was actually a galaxy outside of and beyond the Milky Way. The space-time fabric of the universe, if it's uniformly filled with one or more types of matter and energy, must expand or contract according to these equations. The mathematics tells us, with no ambiguity, that this must occur. But what exactly does expansion or contraction actually mean when it comes to space itself? You see, space itself is not something that's directly measurable. It's not like we can go out and take some space and just perform an experiment on it. Instead, all we can do is observe the effects of space on observable things, like matter, antimatter, and light, and then use that information to figure out what the underlying space itself must be doing to cause those effects. For example, if we go back to the black hole example, although it applies to any mass, we can calculate how severely space is curved in that black hole's vicinity. If the black hole is spinning, we can calculate how significantly space is dragged along with the black hole due to the presence of the black hole's angular momentum. If we then measure what happens to objects in the vicinity of those objects, we can compare what we see with the predictions of general relativity. In other words, we can actually perform experiments to determine whether space curves in the way Einstein's theory tells us it ought to in a wide variety of ways. As soon as the first conflict arises, as soon as a single observation is inconsistent with Einstein's predictions, we will have a compelling case for extending the theory of gravity beyond Einstein's general relativity. But a full 109 years after general relativity was first put forth, that day has not yet arrived. To an incredible level of precision, every observation matches and agrees with general relativity's predictions. Light blue shifts when it enters an area of extreme curvature, and red shifts when it leaves. This gravitational redshift has been measured for stars orbiting black holes, for light traveling vertically in Earth's gravitational field, from the light coming from the sun, and even for light passing through growing galaxy clusters. It's also been measured right here on Earth, as light redshifts when it travels upward in Earth's gravitational field, and blue shifts when it travels downward, closer to Earth's center. Similarly, other predictions such as gravitational time dilation, the bending of light by large masses, and the precession of everything from planetary orbits to rotating spheres sent up to space have all spectacularly agreed with Einstein's predictions. But what about the universe's expansion? When we think about the expanding universe scientifically, the question we should be asking ourselves is, what observably is changing about the things we're capable of measuring in the universe? After all, that's what we can physically predict. That's what's physically observable, and that's what will inform us as to what's actually physically occurring. Anything else is us placing a veneer, a mask reflecting the limits of our own intuition, atop what we actually understand about reality. The modern picture of the expanding universe. The simplest evolving quantity we can consider in an expanding universe is density. If our universe is filled with stuff, then as the universe expands, the volume of the space that this stuff occupies will increase. We normally think about matter as the stuff we're thinking about. Matter is, at its simplest level, a fixed amount of massive stuff that lives within space. As the universe expands, the total amount of stuff remains the same, but the total amount of space for the stuff to live within increases. For matter, density is just mass divided by volume. And so if your mass stays the same while your volume grows, your density should go down. When we do the general relativity calculation, that's exactly consistent with what we find for matter. But even though we have multiple types of matter in the universe, normal matter, black holes, dark matter, neutrinos, etc., not everything in the universe is matter. For example, we also have radiation, quantized into individual entities like matter, but massless, and with its energy defined by its wavelength. As the universe expands, and as light travels through the expanding universe, not only does the volume increase while the number of particles remains the same, but each quantum of radiation experiences a shift in its wavelength toward the redder end of the spectrum, longer wavelengths. This red-shifting effect is how the expanding universe was first detected, and shows up in every galaxy and quasar we measure beyond our own local group. Meanwhile, our universe also possesses dark energy, which is a form of energy that isn't in the form of particles at all, but rather appears to be inherent to the fabric of space itself. While we cannot measure dark energy directly the same way we can measure the wavelength and energy of photons, there is a way to infer its value and properties. By looking at precisely how the red-shifting light from distant objects evolves as a function of distance. Remember that there's a relationship between the different forms of energy in the universe and the expansion rate. When we measure the distance and redshift of various objects throughout cosmic time, they can inform us as to how much dark energy there is, as well as what its properties are. What we find is that the universe is about 2/3 dark energy today, and that the energy density of dark energy doesn't change. As the universe expands, the energy density remains constant. When we put the full picture together from all the different sources of data that we have, a single, mostly consistent picture emerges. Our universe today is expanding at somewhere around 70 kilometers per second per megaparsec, which means that for every megaparsec, or about 3.26 million light-years, of distance, an object is separated from another object. The expanding universe contributes a redshift that's equivalent to a recessional motion of 70 kilometers per second. That's what it's doing today. But by looking to greater and greater distances and measuring the redshifts there, we can learn how the expansion rate differed in the past, and hence, what the universe is made of, not just today, but at any point in history. Today, our universe is made of the following forms of energy. About 0.008% radiation in the form of photons or electromagnetic radiation, about 0.1% neutrinos, which now behave like matter but behaved like radiation early on, when their mass was very small compared to the amount of kinetic energy they possessed, about 4.9% normal matter, which includes atoms, plasmas, black holes, and everything that was once made of protons, neutrons, or electrons, about 27% dark matter, whose nature is still unknown but which must be massive and clumps, clusters, and gravitates like matter, and about 68% dark energy, which behaves as though it's energy inherent to space itself. If we extrapolate backward, based on what we infer about today, we can learn what type of energy dominated the expanding universe at various epochs in cosmic history. And if you can measure the expansion rate today and how it's evolved over time, you can determine what's in your universe right now, as well as what it was like in the past, and how it will evolve into the future. With good enough observations, we can determine our ultimate fate. James Webb deepened the crisis. In cosmology. However, based on multiple observations of stars and galaxies formed James Webb and Hubble, the universe seems to be flying apart faster than our best models of the cosmos predict it should. Evidence of this conundrum has been accumulating for years, causing some researchers to call it a looming crisis in cosmology. As Nobel Laureate Adam Rees, who led the latest effort to test the anomaly, said, "The universe seems to throw a lot of surprises at us, and that's a good thing, because it helps us learn. If the Hubble tension really does reflect our physical reality, then explaining it will probably require adding another item to our list of the universe's fundamental ingredients. One of the leading theoretical contenders, called early dark energy, proposes that about 50,000 years after the Big Bang, there was a brief flare-up of dark energy. In principle, a short blip of extra dark energy could alter the expansion of the early universe enough to resolve the Hubble tension without messing too much with the standard model of cosmology. But in the process, cosmologists' estimates for the age of the universe would fall from the current 13.8 billion years to about 13 billion years. According to Mike Boylan-Colchin, an astrophysicist at the University of Texas at Austin, there's a lot of questions about why you have to introduce this one new thing that just shows up and disappears. That feels a little funny. But we're in a place where, if these things are really that discrepant, maybe we have to start looking in the funny corners of the universe. And in a brand new study published in the journal Classical and Quantum Gravity, Dr. P.K. Suresh and his colleague from the University of Hyderabad, B. Anupama, proposed a solution to align these disparate results. They underscored that physicists infer the Hubble parameter indirectly, employing our universe's evolutionary model based on Einstein's theory of general relativity. The team argued for revising this theory to incorporate quantum effects. These effects, intrinsic to fundamental interactions, encompass random field fluctuations and the spontaneous creation of particles from the vacuum of space. Despite scientists' ability to integrate quantum effects into theories of other fields, quantum gravity remains elusive, making detailed calculations extremely difficult or even impossible. To make matters worse, experimental studies of these effects require reaching temperatures or energies many orders of magnitude higher than those achievable in a lab. Acknowledging these challenges, Suresh and Anupama focused on broad quantum gravity effects common to many proposed theories. Their theoretical exploration revealed that accounting for quantum effects when describing the gravitational interactions in the earliest stage of the universe's expansion, called cosmic inflation, could indeed alter the theory's predictions regarding the properties of the microwave background at present, making the two types of Hubble parameter measurements consistent. Of course, final conclusions can be drawn only when a full-fledged theory of quantum gravity is known, but even the preliminary findings are encouraging. Moreover, the link between the cosmic microwave background and quantum gravitational effects opens the way to experimentally studying these effects in the near future. What is the universe expanding into? Back to the expanding universe. Today, we have every reason to think that our observable universe, whose cosmic horizon is set by a combination of the expansion rate, the speed of light, and the amount of time that's elapsed since the Big Bang, only represents a small fraction of a larger, more complete unobservable universe. The amount that we can see and access has increased over time and will continue to do so as light that was emitted long ago, light that's already on its way to us, will eventually arrive for the first time, despite the continued expansion of space. Given enough time, more than double the present volume of universe will eventually become visible to us. And it's possible, although no one is certain, that this unobservable universe may be truly infinite in extent. It wouldn't make sense if this were so to ask, what's it expanding into? Because it's already infinite, covering every cubic inch of space imaginable. Let's think of the following questions. What's infinity plus infinity? It's still infinity. What do you get if you double, triple, or quadruple infinity? It's still infinity. And what happens if you multiply infinity by infinity, even if you do it in multiple dimensions? You still only get infinity. That's what the expanding universe is like if it's truly infinite. And that's something that even many non-physicists can see for themselves. Is our universe expanding into multiverse? Now, there's no guarantee that the universe is infinite, or even that the unobservable universe represents the full entirety of what's out there. It's possible, as the theory of cosmic inflation strongly suggests, that our universe, large though it may be, is only one region where a Big Bang occurred. Outside of that region is more space where inflation hasn't ended, but continues on and on for perhaps an eternity, and is pockmarked by other pockets where inflation ended and Big Bangs occur. This is commonly known as a multiverse, with no two baby universes ever meeting, colliding, or overlapping. Bottom of form. So, does this mean that our universe is, in some sense, expanding into this inflationary multiverse? The answer, perhaps surprisingly, is no. The biggest difference between a balloon, a ball of dough, and our actual universe is not what's inside or outside of it, nor what its boundaries are, or whether it has them. It's that when we talk about space, or space-time, or the fabric of the universe itself, we're talking about everything that there is. It's the stage upon which the play of the universe takes place. Of course, there are rules. For instance, the players are the particles and antiparticles and other quanta of energy. The governing rules are the laws of physics and the values of the fundamental constants, and the stage itself is not fixed, but rather is an evolving entity, but there's no outside or beyond to the cosmos. It is simply all there is and ever was and ever will be. And that's the biggest thing to wrap your head around. When it comes to the expanding universe, it isn't expanding into anything, because there isn't anything else above, beyond, outside, or before or after space and time. All at once, it's both everything and nothing. Everything because it contains all that exists, and nothing because if you take all the matter, radiation, and quanta that exist within it away, it still persists. The nothingness of empty space itself. That's what the fabric of space-time is, and that's why it can't expand into anything. It itself is a fundamental part of our reality. That's why, when you ask, what is the universe expanding into? The best answer we can give is itself. The key realization is to stop thinking of the universe as a thing that evolves in some larger, greater context. It's perfectly reasonable to think of it as all there is, and to simply recognize that expansion and contraction are properties inherent to space itself. Regardless, we also can't rule out the possibility that there is some higher dimensional perspective that it would make sense to treat our universe as expanding into, just as a two-dimensional surface of a balloon expands in 3 dimensions, but there is no evidence to favor this idea. At present, it's simply one fascinating possibility that cannot be ruled out. But it also isn't necessary. The universe doesn't require something else to expand into. Simply existing and getting less dense is something it can do all on its own. Not everything expands. Moreover, it is worth noting that there are plenty of galaxies that don't obey the equations for the expanding universe, at least not in any sort of an exact fashion. For example, take the galaxies that are bound together inside of a massive galaxy cluster. The closest example we have is the Virgo cluster, located some 55-60 million light-years away. Based on our measurements of the expanding universe and the distance to the Virgo cluster, we'd expect to find the galaxies within it receding from us at approximately 1,200 kilometers per second, give or take. But that's not what we measure when we go ahead and make the critical observations. Inside the Virgo cluster are thousands of galaxies. Some of them are actually headed toward us with a small but measurable blue shift. Most are headed away from us, but around half of the galaxies we find have too low of a speed, between about 0 kilometers per second and 1,000 kilometers per second. Also, about half of the galaxies we find within the Virgo cluster have a greater than predicted redshift of more than 1,200 kilometers per second, and some receding at even more than 2,000 kilometers per second. There's an important reason for this. The galaxies within the Virgo cluster of galaxies are all gravitationally bound to one another and swarm around each other in a beehive-like fashion. We can only easily measure the line of sight motions of these galaxies, the component of their motion that's directed either toward or away from us. The transverse components of their motions, The up and down or left and right motions of these galaxies cannot be measured on mere century-like timescales, as galaxies are far too large and distant to be observed moving in those dimensions. We can only take a momentary snapshot of what's happening right this moment, when the light from these distant objects is arriving at our eyes. So why are these galaxies not obeying Hubble's law, and why are they in violation of the Friedmann equation's predictions? For the same reasons that planets orbit the Sun in the solar system and stars move around the Milky Way inside our galaxy, because they're all mutually bound together through the force of gravity. These gravitational forces imprint what astronomers call a peculiar velocity onto these objects, a speed ranging from hundreds to thousands of kilometers per second that gets superimposed on top of the Hubble flow. All of space-time doesn't exhibit the same behavior because some systems are bound, gravitationally or otherwise, while others are unbound, and it's only the unbound systems that experience the expansion of the universe. Are we expanding along with the universe? The big question we need to ask ourselves, whenever we're considering what governs the behavior of space, is the question of what is governing the shape, curvature, and evolution of space-time on the scales we're considering. Even though we're part of the expanding universe, most of what we're familiar with is not itself expanding. Atoms bound together by the electromagnetic force do not expand. Human beings, also bound together by electromagnetism, do not expand with the expanding universe. Features on planet Earth, which is bound together by gravity, do not expand with the expanding universe. However, if the Earth physically expands due to factors like thermal expansion or core activity, then those features would expand. The Earth-Sun distance, again determined by gravity, does not expand as the universe expands. As the Sun loses mass, however, the Earth-Moon system spirals outward. A different effect dominates here. The distance between stars within the Milky Way, which is gravitationally bound, doesn't expand as the universe expands. And the distance between the Milky Way and the other galaxies in the local group, which again is bound by gravity, doesn't expand as the universe expands. It's only once you get to a scale that's larger than the largest bound structure you're considering, structures larger than galaxies, galaxy groups, and galaxy clusters, that the expansion of the universe plays a role in what you observe. You may notice a curious omission from the list of bound structures above: galactic superclusters. It turns out that the largest a bound structure can be in our universe, as far as we understand it, is somewhere between about 1 and 2 billion light-years, no larger. The largest galaxy clusters are about this scale, as are a few galactic walls. However, no structures larger than this should be gravitationally bound in our dark energy-dominated universe. This includes our own home supercluster, Laniakea, as well as purported quasar and gamma-ray burst associations, which we cannot scrupulously call structures in their own right, as they are certainly expanding and are not bound, either gravitationally or through any other mechanism. The individual structures that we're familiar with, including atoms, humans, planets, stars, galaxies, and even groups and clusters of galaxies, are not expanding along with the expanding universe. It's only the space that exists in between the largest bound structures that appear on any scale, between unbound galaxies, galaxy groups, or galaxy clusters, that exhibits the behavior of the expanding universe. As physicist Richard Price quipped, "Your waistline may be spreading, but you can't blame it on the expansion of the universe." That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.